Okay, hello everyone. In this session, we are going to discuss about laser. Laser stands for laser stands for light amplification by stimulated emission of radiation. Comparing with ordinary light, laser is having high intensity, monochromatic, and it is collimated. So there are basic concepts about laser. The basic concepts are comparing with the ordinary light, how we are getting continuous emission of light in the laser. For that, there are two energy levels. One is ground state, another one is excited state. See, normally in the ground state, the number of atoms present is denoted by N1, and in the excited state is denoted by N2. Here, there will be number of atoms. If the atoms in the ground state having sufficient energy, it can goes to excited state by its own. But it is not possible for all the atoms, since if they are not getting or they are not having sufficient energy, then it can regain in the same state. For that, we have to stimulate it by means of some external photon. For example, if the external photon is having energy E is equal to h nu, when it is triggered by some external photon, all the atoms present in the ground state is not absorbing the external photon. There are some condition. The condition is actually this is, we can say, del E equal to h nu. The del E is nothing but difference between two energy levels, E2 minus E1, which is equal to h nu. When we use the external photon to trigger the atoms in the ground state, it should obey the condition of E2 minus E1 equal to h nu. Then only it can absorb. That is, the atom or molecules present in the ground state can absorb the external photon when it obeys the condition of this. Then only it can goes to excited state. When it reach the excited state, in which also there are two important mechanisms that we have to understand in detail. First one is called fluorescence. And second one is phosphorescence. So we should know what is fluorescence. See, normally the atom or molecules in the excited state can stay up to 10 power minus 8 second. So in the excited state, it can stay up to 10 power minus 8 second. After that, what will happen means it will come back to ground state. So this is the regular process. During that transition, if it can radiate, that is what laser output. But it is not possible in all conditions. Anyway, fluorescence means the atom or molecules in the excited state can come back to ground state within 10 power minus 8 second. If not, it can stay some more time. In case if it is delays, then we can say that process is called phosphorescence. So the phosphorescence also defined as the delayed fluorescence. So these two mechanisms are very important. We have to understand about the laser concepts. So the first concept in the laser action is stimulated absorption. Stimulated absorption. That's why I have explained about the fluorescence as well as phosphorescence. So, what is stimulated absorption? As I mentioned earlier, the atom or molecules in the ground state cannot absorb all the external photons. So, it should be triggered by external photon, and it should, obeying the condition of this, can absorb the atom. Say for example, if this atom or molecules absorb this external photon and gain sufficient energy, then it goes to excited state. So, that is what stimulated absorption. And the second concept is spontaneous emission. Spontaneous emission. So, spontaneous emission means when the atom or molecules goes to excited state by absorbing the external photon, can stays up to 10 power minus 8 second or even more that, then it should come back to ground state. So, we can say, we can classify like when the atom or molecules goes to excited state called upward transition, the atom or molecules coming back to ground state is called downward transition. So, in the downward transition, if it is able to radiate the laser as output, then we can say spontaneous emission. Then the third process, most of the atom or molecules can undergo spontaneous emission since it goes to excited state by absorbing external photons so that it gains more energy. In some cases, it is not emitting as laser, then it should be furtherly triggered by external photon, then we can say it is stimulated emission. So, these three processes are very important to understand any laser actions. So, in this, now we have to understand the remaining laser action mechanisms. Then the condition, actually the two important concept is normal population. So, what is normal population? So, normal population means in the ground state the number of atom or molecules are more than excited state, then we can say it is normal population. Second condition is population inversion. Population inversion. So, population inversion means the atom or molecules in the excited state is greater than ground state. Now, you can clearly understand, mostly in the normal population we could not achieve any laser action. So, we have to trigger it by means of some external agency called photon, then it goes to excited state. That is what we said, upward transition, then it stays up to 10 power minus 8 second, then it will come back, and that transition is called downward transition, and that process is called phosphorescence. So, this is what we have to understand clearly. And for any laser action, it should attain the population inversion. So, that is very important. So, for population inversion, there are some conditions. The first condition is it requires minimum 2 energy levels. So, this is what 2 energy levels: ground state, excited state. So, it requires minimum 2 energy level to achieve any population inversion condition. Second, it should be continuously triggered, or it requires some continuous energy. That is how we can achieve the population inversion. So, these two conditions are very important to achieve the population inversion, and once you achieve the population inversion, then it is very easy to achieve the laser action. There are some more energy levels, we can say one more energy level, that is called a metastable state. So normally for laser action it requires 2 energy level. Furtherly we have one more energy level, we can say it is metastable state. It is to achieve further laser action, metastable state. So in the metastable state what will happen means the atom or molecules goes to excited state like upward transition, then after 10 power minus 8 second it will come back. In the 3 energy level state what will happen means the atom or molecules in the excited state coming back to metastable state, it stays sometimes and it acquires sufficient energy. So here also you have to understand very important point, that external photon can be triggered continuously. We can imagine like a balls, it goes up, so it moves like this, then this photon coming and it approach very close to this, if it collide then it gains more energy, then it goes to exit state. Then during downward transition also the external photons coming back and it can collide with this. During this transition also if it gains more energy, definitely according to law of conservation of energy it should release. So during this transition it can radiate, or in some cases during this transition also it can radiate. Most of the cases when it transfer from E2 to E3 it can radiate the laser. We have one more energy level, we can say it is E4. So 4 level laser also there. So we have 2 energy level laser, 3 energy level laser, 4 energy level laser based on the different types of lasers. So these are the basic concepts in the laser actions. Then we can discuss about the types. There are so many types of laser. Initially it was invented by T.H. Maiman in 1960. He is the starting point for all the laser process. First type is solid laser, second one is liquid laser, third we have gas laser also, semiconductor laser, and dye lasers. Still we have some more lasers also, but most of the lasers are coming under this solid, liquid, gas, semiconductor and dye lasers. So these are the basic concepts about laser actions, in which the important point is stimulated absorption, spontaneous emission, stimulated emission, and normal population, population inversion. We have mentioned about fluorescence and phosphorescence. So these are the important point, and by understanding these concepts then we can understand the actual mechanism of laser in detail. Now components of lasers, components of laser. So there are 3 basic components. Of course we have more components. First component is active medium, active medium. Second one is resonant cavity, resonant cavity. Third, pumping action. So these 3 are important components for any lasers. First we have to discuss about active medium. See in any type of lasers like solid, liquid, gas, semiconductor, dye, see we have to achieve the population inversion. As I mentioned earlier, without population inversion we couldn't achieve laser action. So to achieve any population inversion we need some material that will differ based on the types of laser we are using, and that material is called active medium. For example, if you take solid laser, there are different types of solid lasers, like we have a NdOG laser, NdOG laser, ruby laser, and we have some more solid laser also. In NDIAG as well as Ruby, so if you take Ruby laser, Ruby rod is the active medium. So simply we can say active medium is the medium in which laser action takes place by achieving population inversion. So that's what active medium. Then resonant cavity. See, if you can understand the laser action based on that energy level which we have already explained. See, in the laser setup, there will be two mirrors. You can imagine like the atom or molecules in the ground state goes to excited state by means of some external photon. That's what we have already explained. And during downward transition, it can be triggered. But the resonant cavity means it has two mirrors. One is 100% reflecting mirror, another one is 50% reflecting mirror, like this. So this is 100% reflecting mirror. So the atom or molecules transits up and downward. If it gets sufficient energy from the downward transition, then it can try to come out through the 50% or partially reflecting mirror. So for, you can imagine like it's like a holes, it's for understanding. So through that the atom or molecules coming out, then we can say that is laser. If not, what will happen? It can bounce back on the remaining portions and it will come back here. And here we have a 100% reflecting mirror, so it will reflect all the atom or molecules which no incident on this. So these two plays very important role. That's what we can say it is resonant cavity. So for all laser actions, resonant cavity is very important. Through the 50% or we can say partially reflecting mirror, we will get the output. So that's why it is resonant cavity. And the third important part is pumping action. So as we explained in the basic concepts, we know the atom or molecules should transist to excited state by means of some external agency, or we can say we are triggering it. That mechanism is called pumping action. So pumping action is to achieve the population inversion or to excite the atom or molecules which is in the ground state and which is not having sufficient energy to goes to excited state. See, naturally some atom or molecules can goes to excited state by its own energy. If not, then it should be triggered by some external agency called photon that should have energy E equal to h nu. Now we can discuss about the pumping action in detail, and it will also differ based on the type of laser which we have mentioned here. Then methods of pumping actions. Methods of pumping action. There are different types of pumping action or pumping methods. First one is optical pumping. Second one, electric discharge. Third, inelastic collision between the atom. Inelastic collision between the atoms. Fourth, direct conversion. Fifth, chemical process. Chemical process. So these five methods are very important to achieve the pumping action. First, we can discuss about optical pumping. See, we know the beauty of physics is it has meaning in the term itself. So in most of the physical terms, it has meaning in the term itself. If you take optical pumping, optic means light. It is applicable in most of the solid type lasers. As I mentioned earlier, like NDR rod as well as Ruby rod, it is surrounded by some flash tubes. For example, you can take a xenon flash tube or krypton flash tube. So when it is subjected to uh, providing electric field, we can make the light to glow. Because of that, the atom or molecules in the ground state can goes to excited state. So that is called optical pumping. Simply we can say by means of light you can achieve the population inversion, then we can say it is optical pumping. It is applicable in solid type of lasers. Then second one is electric discharge. So electric discharge also takes place in gas lasers like CO2 laser. So in which there are two different energy levels. For example, this is atom 1 and this is atom 2. It goes to excited state, it goes to excited state. So here or CO2 or helium neon laser also there. Helium neon, if you assume this is helium atom and this is neon atom. So helium atom goes to excited state, neon atom can goes to excited state, it stays here, it stays here, and it can collide each other. Because of this collision, it acquires sufficient energy to comes out as laser. So that's what electric discharge. So here also by means of electric field you are going to achieve the population inversion, that's why it is electric discharge. Then yeah, similarly inelastic collision between the atom also takes place in the same way, or in other words simply we can say by applying electric field itself we can achieve the population inversion, that is electric discharge. Inelastic collision, this is what you can refer the same, the atom or molecules goes to excited state and it collide each other. Then fourth one is direct conversion. So direct conversion takes place in most of the semiconductor lasers. So in semiconductor lasers, recombination takes place. Recombination takes place. So recombination means we know that the electrons in the conduction band, holes in the valence band combine each other, then it gets sufficient energy, it comes out as output. That is what recombination process. Then finally chemical process. So chemical process takes place in dye lasers. So let me repeat again, for solid lasers, optical pumping plays very important role. Electric discharge, like even in the gas laser as well as in solid also. Simply we can understand like in the electric discharge, by providing electric field, you can excite the atom or molecules and it achieve the population motion. That is electric discharge. Inelastic collision between the atom means like two different atoms are there, it goes to excited state, it undergoes a collision, that is inelastic collision between the atoms. Direct conversion, so recombination process takes place, and chemical process, there will be some chemical reaction especially in the dye lasers. So these are the methods of pumping action for any laser actions. Now we can discuss about semiconductor laser. There are different types of lasers. So in this session we can discuss about semiconductor laser. In the semiconductor laser, just now we have discussed about the pumping action, pumping method. So direct conversion takes place. So direct conversion means we know the electrons in the conduction band occupies the holes in the valence band. So semiconductor laser, it's furtherly classified into two types such as homojunction semiconductor laser, heterojunction semiconductor laser. Heterojunction semiconductor laser. So there are two types, homojunction, heterojunction semiconductor laser. So in this, first we can discuss about homojunction semiconductor lasers. As I mentioned earlier, it has meaning in the term itself. Homo means same. If you are using both the layers, see most of the semiconducting materials like diode, it has two regions, P region, N region. So you can assume like this. So there are two regions, this is P region and this is N region. So if these two regions are made up of same material, homo means same material, then we can say it is homojunction. So for that we can use gallium arsenide, gallium arsenide. So both the materials are gallium arsenide, and it is connected with electrode. So like this we have to connect. When it is subjected to forward bias, so we know forward bias means the P region connected with the positive terminal of the battery, N region connected with the negative terminal of the battery, then recombination takes place. So we know in the N region the majority charge carriers are electrons, the P region majority charge carriers are holes. So when forward bias takes place, we know forward bias means the depletion region becomes very narrow. So during that process, the electron occupy the holes and it combine together, and it gives some external or extra energy as output. So this is how the homojunction laser works. But still, in the basic components we have discussed about the resonant cavity. In the semiconductor laser, especially in the homojunction semiconductor laser, one side is, say for example here you are getting output, this side is completely polished. So it acts as 50, okay, here we can get output, another side act as 100% reflecting mirror. So through this we will get the output. Here the atom or molecules bounce back and we will get the output. So this is homojunction semiconductor laser. See, in the homojunction semiconductor laser, the output is mostly continuous, or even if you want pulsed type also we can get the output. But if you want to get only continuous output, then we can go with the heterojunction semiconductor laser. So in the heterojunction semiconductor laser, the only change is, instead of two regions, we have to use different regions. There are 5 regions in the heterojunction semiconductor laser. In this also, the first 3 regions are P region, and last 2 regions are N region. And again, like homojunction, you can assume like in the right hand side we are going to get output, which means it is 50% polished and this is 100% polished. And here the first region is made up of gallium arsenide, means second one is gallium aluminum arsenide, third again gallium arsenide, fourth gallium arsenide, and fifth gallium aluminum arsenide. So that's how they are arranged, like the alternate materials, or we can say different materials. So hetero means different materials. So homo means both the regions are made up of same material. Heterojunction, it's made up of different material. So first layer is made up of gallium arsenide, second layer is made up of gallium aluminum arsenide, third layer is gallium arsenide, fourth again gallium arsenide, and the fifth one again I think yeah, we have written little more, or we can write like they are all alternates, gallium aluminum arsenide and again gallium arsenide. So like this it should be arranged. So this type of arrangement is very difficult. That is one of the disadvantage of no heterojunction semiconductor laser. However, we can get output continuously, since in the homojunction we can get both continuous output as well as no pulsed output. So here normally the thickness of crystal is like gallium arsenide materials, it's like 0.5 or even smaller than that also. So like this we have to arrange. This is very difficult process. Again the working processes like recombination takes place when it is subjected to forward bias, then we will get the output. In both the homojunction as well as heterojunction semiconductor laser, how we can determine the wavelength of light emitted is using this formula E equal to h nu. Here I have mentioned EG is nothing but band gaps. See this band gap we should understand in the semiconducting process, like we know there are two types of bands. One is valence band, another one is conduction band. The separation between the valence band and conduction band is called a band gap. So this is the basic idea. Using this condition here also for both, what will happen means, this is the energy level diagram for homojunction as well as heterojunction semiconductor laser. See here this is valence band and this is conduction band. In the valence band the majority charge carriers are holes, sorry electrons, sorry, holes. In the conduction band the majority charge carriers are electrons. So make it clear, in the valence band the majority charge carriers are holes, in the conduction band the majority charge carriers are electrons. So when it is subjected to forward bias, recombination takes place, then we will get the laser as output. So now we can use this formula E equal to h nu, and we know nu is c by lambda. If you know the band gap value, then it is very easy to determine the wavelength of laser light emitted by the particular laser. By rearranging this equation, we know lambda is equal to hc by Eg, where h is the Planck constant, c is the velocity of light. So if you know the band gap value, then it is very easy to find out the wavelength of light emitted by the particular laser. So this is how we can get or we can determine the wavelength of light emitted by the particular laser. So this is regarding homojunction and heterojunction semiconductor laser. And still we have a solid laser, liquid laser, dye laser, gas laser and so on. There are some common applications of all the lasers, but the application differs based on the different types of lasers. The common application is lasers are used in communications, printers, even in the medical field also. In industry, the lasers are used for welding, cutting and drilling.